Alright, so here's where we stop, Mathlete. So those are the things we're going to use. You've used a lot of this. Maybe if you memorize that, that's fine. You just throw those things in instead. It's the same stuff. Here we go. Alright, some of you love the pottery. Fabulous. So let's spin some pottery. 10, this is revolutions per minute, not radians per minute. It's just what we do here in America. What is the angular acceleration of that? Okay. So remember our little formula for this. I know how much you guys love my mouse. So here we go. So angular acceleration, it's the final W looking thing minus the initial W looking thing divided by the time thing. And there you go. It's 30 seconds. Do the easy stuff first. Bam! There it is. From rest, so oops, this is the initial, so I can put that sub naught for the college types. It's a little large, but yep, so am I. So minus 0. Now I have to have this. Guys, we're in radians per second, not revolutions per minute. So here comes the arduous task of conversions. Ugh. Revolutions per minute. Alright, that's an N. Okay. So, put a minute on the top. 1 minute. That's an M-I-N. Okay. 60 seconds on the bottom. Now I'm in seconds. Hallelujah. Get rid of those revolutions. So I put the revolutions on the bottom. 1 revolution on the bottom. 2 pi or 6.28 radians on top. Alrighty. Where's that calculator? Here we go. 10 divided by 60 times 6.28. Boom, chakalaka. 1.05. I'm rounding off and yeah. Jimmy crack corn, and I don't care. That's close enough. 1.05, and that is in radians per second because my revolutions canceled out, and I got radians there per second there. So it's 1.05. Yep, that sounds about right. Things don't happen too fast in pottery class because otherwise your clay gets everywhere. Alrighty, so divide that by 30, and that's a whopping 0.035 radians per second squared. Alright, sweet. How many revolutions did it undergo to another? Oh my goodness. Do you want to do this easy way or the hard way? Let's start the easy way. Okay, great. We'll do it the easy way. Well, remember how I always did things the easy way by doing this x equals the V average times the time? I'm going to do that same thing. Except I'm going to do it it's in revolutions. Well, I'll do it in radians first. Okay. I'm going to do the same thing. I'm doing my angular displacement, but I'm going to use my average. So I'm going from 0 to 1.05, so I got to divide by 2. So I got to, it's the 1.05 plus 0 technically, divided by 2, because remember I started at 0. So that's the average angular velocity. Angular velocity, the W, it's not a V, it's the W looking thing, the angular velocity, and the times is the 30 seconds. Okay, so to me that's just the easy way to do that. So there it is, 1.05 divided by 2 times 30 seconds, and I got my 15.75. Okay, that's in radians. I was going to round that off, but I'll save my rounding because that's not the final answer. That's in radians. These suckers are insisting that I go to revolutions. Alrighty. So, times 1 revolution per 6.28 radian. So that goes on the bottom. So divide by 6.28 and bam, 2.5 revolutions. All right, I can live with that. So in 30 seconds, it goes around 2.5 times. How exciting is that, sitting at the pottery wheel? In half a minute, it makes 2.5 turns. Woohoo! Party on, Wayne. Alrighty, let's check the answer machine. Alright, they're nailing that one. Look at that. They think they're better than me going 1 extra sig fig. And once again, going 1 extra sig fig, they think they're better than me. Except they only have 1 sig fig up here to begin with. So they're totally blowing it. Alrighty. I don't think they understand sig figs. That apple thinks he knows what's going on. I think the apple only knows how to ring that bell. Go work for Salvation Army. Alrighty. So linear movement about a rotation. Okay, so I think so these are some time-saving things, people. So a lot of you know how to find displacements, velocities, and accelerations. This is a quick and easy way to convert it to the angular component. Okay? All you have to do is take the linear divided by the radius, and you're already in that component in your radians. Okay, if you divided the linear component by the radius. Or if you have the angular in the radians times the radius, now you're in the meters. If you have your radians per second times the radius, you're in the meters per second. If you have your radians per second squared times the radius, you're into the meters per second squared. So those are the quick ways to go between your linear and your tangential. And you might say, but if you go into a circle, how do you have a linear? Well, you don't. It's the magnitude. Okay? It's the magnitude. This is the speed, not the actual velocity. It's the magnitude of the acceleration, not the direction. It's not the displacement, it's actually the distance. So these are the magnitudes of the amount, not the actual vector amounts. Okay? All right. And it only works when you're in radians. So these have to be in radians for that to happen. Alrighty, I think we're about done with the math here, but this might wrap it up here. Coin radius is initially rolling with blah, blah, blah. Speed of that comes to rest. Experience slowing down of that. Over what angle? Well, guys, you have, okay, so you have a radius. You have a speed, an initial speed, and a final speed. And you have an angular deceleration. So how would you find the angle did the coin rotate? Okay, so we do not have a time here. If you want to do this in one equation, which one might that be? If you don't have a time that this all happens in. Could it be this one squared equals this one squared initial plus 2 fishy symbol and angle symbol? Does that look familiar? Something like that? Alrighty, so what we're solving for is what again? Oh, this angle thingy. Okay, so what that means is we got to do the final squared minus the initial squared. I'm just minusing that from both sides. I'm going to take a couple quick steps here, guys, because I got stuff to do tonight if I go to bed. I got to divide out by the 2 alpha on both sides. So I'm dividing out by the 2 alpha. And then all I have left is my theta, and that's going to be actually already in radians. Oh, well, this is working out easier than I thought. So remember, that's the final, that's 0. 0 minus the initial is 3. Don't forget to square it. I'm going to leave off my units, guys. I'm writing with my mouse. And I'm already in the right units anyway, so I'll be fine. I'm in radians per second already. 2 times 0.05. And that's in radians per second squared. So it's all going to work out to be in radians. All right. So I can do this in my head, guys. So it's going to be a negative. No, it's not going to be a negative. See, that shouldn't come out to be negative because this is a negative acceleration, guys, because we're slowing down. Because we're going in the forward direction, so we shouldn't have a negative displacement here. So long story short, I get a -9 on top. I've got a -0.1 on the bottom. That means this is 90, right? Hey, man, brother. Thanks. So that is 90 radians it's moved through, huh? Isn't that impressive? 90 radians. So what linear distance? Oh, well, remember that little trick with the x equals the r times that theta, that thing we just looked at? And you don't have to memorize that. This is a conversion, guys. So if this is 90 radians, all I'm doing is a conversion here. That's not a v, it's an r. So I got to divide out by the radians. And I need a distance in meters. And if we go through 1 radian, what distance do you go through, guys? Oh, it's 1 radius of 1.5 centimeters, but make sure I'm in meters here. You know what? Forget that, Jack. I'm going to be in centimeters. I am going to be a rebel. Look at that. 1.5 centimeters. I'm not converting anything. Convert this. So 1.5, so that's 45. That's 135 centimeters. Look at that. Huh? 135 centimeters is how far the thing traveled and slowing down to a stop. Isn't that fun, guys? Yeah, fun comes in all different sizes, doesn't it? All right, 90 radians, nailing life there. 135 centimeters. Ha! They did the same thing. They weren't a bunch of suckers and converted it to meters. Alrighty. Oh my goodness. I thought we were done, guys. Well, alrighty. Get out your pencils. Still not done. You're just getting warmed up, it looks like. Guys, this first part looks like it's going to be a little review, some triple acceleration, and then we'll just go through all this other stuff. It's good fun anyway in the end. And we've got a couple minutes left anyway there. So, race car accelerates uniformly from 40 to 60 in 5 seconds. Around a circular track of 400 meters, and the car reaches a speed of 50 meters per second. Find the centripetal acceleration. Well, guys, this is kind of an oldie, but a goldie. I don't know if it was that gold, but centripetal acceleration is just your v squared, your speed divided by your r. So you're just squaring your 50. Oh, I don't know where that line came from. I did not put that in there. And divided by the r. Where's the r? 400. So 5 times 5 is 25, and add 2 zeros onto there. And then divide by 400. Oh, this is not going to come out even, guys. Okay, 4 goes into there 6 times. And I have a 4th left over. So it looks like 6.25. Am I nailing it? Yeah, 6.25 then. Okay, 6.25 meters per second squared. Are we going to be out of time here? I'm going to have to go to a whole another video to get this all on YouTube. So remember that answer, because I'm not doing this one again. That is 6.25, and I don't need that to do these others again anyway. So that works out just fine. That was just a little bit of review for you. Then we'll just race through all these others. And remember, That's 6.25 for the angular, and we'll find those others. All right, see you in a bit.